Hello and welcome back to Calculus 1, section 2.5 on limits at infinity. Not to be confused with infinite limits. So limits at infinity. We are going to take a look at the limit as x goes to one of the infinities and then look for an answer. So I hope you see that this is completely backwards than what we had previously, right? Previously, x went to finite number a, and we were looking for answer to be infinity. Now, the x goes to infinity, and we are looking for a finite answer on the other end. So this is the type. There's another type we'll talk about, but this is generally what we want to know. So, good example to discuss right off the bat to show this would be e to the x, right? So if I have limit x goes to negative infinity of e to the x, the answer would be 0. Because when you draw e to the x, it goes through 1. You are supposed to go to negative infinity. So as you are going on x-axis to negative infinity, you observe the y value of the black line of the graph dropping down to 0. Do we all see that? So as x goes to negative infinity all the way to the left, your y value goes down to 0. And the limit is 0. Eventually, in calculus courses and the differential equations courses, for those of you who take them, you will talk about logistic function for exponential functions, where you might talk about population. People, frogs, bacteria, doesn't matter. And you might run into a graph that looks like this. Initial population P0, exponential growth, and then it levels off at some value capital K. Usually this is a time axis, and this is the population axis. So if you look at this particular graph, the limit of p of t, which is a function, as t goes to infinity, is going to be k. K stands for carrying capacity. You see, this planet is of the finite size. Finite size means finite surface area for, let's pick humans, to live on. Humans don't live on water or under the water. Vast majority of humans do not live in deserts or ice caps. So we need kind of particular environment to be comfortable and prosperous, right? So deserts are not good. Ice caps and ice and crazy snow is not good. Not that we don't have anyone there. We do have, right? People do live in deserts. People do live in Alaska and poles and Sweden, right? But most of the people don't live there in those extreme places. So planet has a finite size, and planet has finite area for us to build houses, to plant our food and let the livestock run around also for food and so on. So there is just so much that the planet can provide in terms of the amount of people that we can have around. And that's what the carrying capacity is for. The maximum amount of people that the planet can sustain with the resources that the planet has. Depending on which study you read, that number is anywhere from 10 billion to 15 billion people. We are in a 7.5. Practically doubled population in the last 20, 30 years, or 40 years, something like that. We doubled the population. So once the population of, let's say, people hits the carrying capacity of the planet, which is the maximum amount the planet can support, we can't go past that. That would be the limit. Because there will be no resources, there will be no food, there will be no available land to build another house, another apartment, to put another trailer or anything for anyone to live. So when you are looking at this, if you are to let time go to infinity, then the amount of people, which is the population, would never exceed this limiting number k. So now you see another example where, and this is applied example, where something like this could be useful, right? So when you look at both of these examples, the e to the x up there and the population one on the bottom, what you see is that there is this horizontal line that y values are approaching. And from there, we conclude that this limit is perfect for defining the horizontal asymptote that you learned about in your pre-calculus class. So now we get to the point where we say horizontal asymptote, and we'll say a horizontal line at y equals L is called a horizontal asymptote if the limit x goes to positive or negative infinity of f of x is equal to that L. So it's a limit definition for our asymptote. Now, it could be positive infinity or negative infinity. Look at the e to the x. If e to the x, if you look at the positive infinity, it's not going to go to any number, right? But the left side did. So the x-axis, y equals 0, is horizontal asymptote for it. Please remember that for vertical asymptotes and horizontal asymptotes, you need one of the limits to be true. You don't have to have both of them to be true. So in my case, over here, as you can see, as this goes to positive infinity, it reaches value k, which is the y value. On this case, as you go to negative infinity, the y value drops down to 0, right? Because this is getting smaller and smaller and smaller and smaller and smaller, so the y value diminishes down into 0. So you can have one or the other. You can have both, sure, right? So one or the other or both. If any one of them fits this definition, the line you have there, the value gives you the line, which we call horizontal asymptote. Please make a note right now that functions can cross horizontal asymptotes. Functions can cross. So let me talk briefly about that. We'll talk much more about that in chapter 4. But it's good to at least have some sense and, you know, keep this in the back of your mind. So functions can cross horizontal asymptotes, AJ. And I'll give you the example right here where you have two vertical asymptotes and a horizontal asymptote here. So you have this, this, and this. So you see that the horizontal asymptotes are obeyed at negative infinity and positive infinity. The function follows horizontal asymptote. So negative infinity all the way to the left, positive infinity all the way to the right. The function bends so that it follows horizontal asymptote. Horizontal asymptotes have to be obeyed at infinities because at x goes to infinities, because that was the definition of it. Now look in the middle. You see that the function pierces right through x equals 0. So it crosses it. So I asked you to write the sentence for vertical asymptotes, and I said vertical asymptotes can never be crossed. That was the previous lecture. Nowhere. Vertical asymptote is the vertical barrier, cannot be crossed by a function at any value anywhere. A horizontal asymptote can be pierced. And you get to obey the asymptote only at infinities. So this is horizontal asymptote. Now, you worked on horizontal asymptotes in your pre-calc course only for rational functions. And they made you memorize those 3 rules that you don't remember, right? The exponent on the top is bigger than the exponent on the bottom, or they're the same, or right, and then, right? You don't remember that stuff, which is good. You don't need it. We have a definition now. Don't even bother remembering it. This was orange, right? So let's take a look at a problem. So limit of x squared plus 3 divided by the limit of 3x squared plus x plus 1 as x goes to infinity. Now, let's say you remember. Let's say you remember your pre-calc 1. You would immediately know that the answer to this is 1/3. Because if I'm asking for the limit as x goes to infinity, I'm looking for horizontal asymptote. Great. And you memorize the rule. When the exponents are the same, it's the ratio of coefficient. So both are squared. Top has 1, bottom has 3. 1 divided by 3. So the answer is 1/3. Done, right? But the question is, do you remember the rules? Right? Do you remember the rules? And we established you don't. So we are stuck with a limit, and we have to solve this limit. Now I need you to mark this because this is going to be your procedure. The way to find the limit for x goes to infinity when you have polynomial divided by polynomial is to divide with the x with the highest exponent. So each one of these gets divided by x squared. X squared is the largest polynomial term. It's a leading term, right? And you divide every term of both of these polynomials with x squared. Now, what happens in the next step is some of these cancel. So now I have 1 plus 3 over x squared x squared and x squared cancel, so I have 3 plus 1 over x plus 1 over x squared. So we use just some rudimentary algebra there. The question is, how much is 1 divided by infinity? Because you have to take, you're dividing 1 by x, but x tends to go to infinity. So what is the answer if you are dividing by infinity? What do we get? What do you think? Yeah. All right, so here's 1. Do we all agree that this is 1? It's 1, right? We can do it with a piece of clothing or anything else, but let's do it with a paper. So do we all agree that this is 1? Let me divide this 1 by 2 and take a look at the answer. So here's my division process. I take this piece of paper and I divide this piece of paper by 2, obtaining this as an answer. Do we all agree that if this is 1, when I divide by 2, I get this? Do we all agree on that? Do we also agree that this is smaller than that? Good. Now, what happens if I take 1 and I divide it by 4? Well, that means that dividing it by 4, I just need to cut this in half. The answer would be this much. So if I took 1 and I divide it by 4, the answer is smaller than before. All right, fine. Let's divide by 8. What's happening with my answer now? You see, where is this going? As I keep dividing by 16 now. So when I divide by 16, the answer is this much. 1 over 16. Divide by 32. There are 32 pieces like this in here. This was 1. This is 1. And then 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 4 times 8, 32 of these, right? Divide by 64. So what happens as this number is 1 for the full piece of paper, is 2 for the half, is 4. What happens as this number goes 1, 2, 4, 8, 16, 32, 64, 128? What is happening with the answer as this goes to infinity? Where is the answer going? Here.
Towards 0.
Towards 0. Divided by infinity, right? Nothing there. So, it's hard to do magic, by the way. So we understand now that limit, as x goes to any of the infinities, of 1 over x to any power p is always going to be 0. I can't stress enough this formula. The rest of your calculus life, you will be using this. If you take anything and cut it infinitely many times, you will arrive at 0. Okay? How many of you get annoyed when you go to some kid's party for a birthday or something, and then they give you those tiny slices of pizza? That's 1/16. There you go, right there. 1/16. If they keep cutting that, you end up with nothing. Right? So now going back to my problem, I just learned that each one of these goes to 0 because of the formula. Each one. If I take 3 papers and rip them infinitely many times, nothing. Right? If I take 1 paper, well, we did the experiment and we got to 128 pieces. 128 of these to make that piece of paper. 256, 512, 1024 of these to make 1 paper. So, when you solve this now, all of these guys went to 0, and there's your 1/3. So you don't have to memorize those rules from pre-calc anymore. You have to remember them. Those rules that say the top is bigger exponent, the bottom is bigger exponent. No, you just plow through this calculation. The number comes out on the other end, and that's it. Now, there is more to this. Not just the asymptote. Another concept you studied in your pre-calc course is called the end behavior of the function. I will start with example and then give you the rules. So we had our good old f of x equals e to the x. And I draw e to the x here. Going through 1. And what do we have? Well, on this side, let's go orange. Over here, we have limit as x goes to negative infinity of e to the x is equal to 0. We established that already. That was clear. As x goes to negative infinity, the y value falls down into 0. So that's that. What's happening on the other side? On the other side, we have the limit of x goes to positive infinity of e to the x, and the answer is positive infinity. This is the end behavior. So we have 4 possibilities. I'll draw them in a chart like this. We have function ends to be one of these. This one is limit x goes to positive infinity of f of x, and the answer is positive infinity. This one is limit x goes to positive infinity of f of x to give us negative infinity. This one is limit x goes to negative infinity, because x goes to the left, of f of x is equal to negative infinity. And limit x goes to negative infinity of f of x is equal to positive infinity, like that. Technically, each one of these motions is broken into pieces. Let's say this one. So you have this arrow, right, is technically that one, and as you can see, this one is broken into this and this, right? The arrow goes down, so that's negative infinity on y, and it goes to the left, which is negative infinity on x. And you can see them both being negative infinity. If you're talking about this arrow here, it looks like that. It goes forever down and forever to the right. So you have positive infinity for x and negative infinity for y. Negative infinity on y, positive infinity on x. These are not arbitrary things for you to memorize. This is simply the picture, right, which follows where the arrow goes. So this arrow goes forever to the right and forever up. Therefore, both are positive infinities, because this way, right, is plus infinity for x, and this way is plus infinity for y. So this quadrant will have both of them positive infinities, and just, you know, go one by one and make sure they all fit. So now you can answer a complete question from pre-calc 1 having this really sturdy foundation. Vertical asymptote, horizontal asymptote, and behavior all together. There's one more type of asymptote that it's out there. It's rare, but it's there. Who wants to be a millionaire? What's that asymptote? Did anyone take pre-calc? You're smiling, so you did, right? You somewhat? You barely took pre-calc. Okay. I had no clue that they would allow to sign up in Calc 1 with a barely took pre-calc person. I guess. You just have to. It's slant asymptote, also known as oblique asymptote. And it's very rare, and it only happens in one case. So, one case for oblique asymptote. It will pop up again in chapter 4. I'm just going to mention it now and just completely ignore it for the rest of the time. Slant asymptote. Also known as oblique asymptote. Occurs only in rational functions where x to the p divided by x to the q and q plus 1 is p. So if the degree of the leading term in the numerator is by 1 less than the degree of the leading term in the denominator, you have oblique asymptote, and we use long division to find it. There we go. More on this when we need them, and that would be somewhere in chapter 4. They shovel the sections around, maybe 4.4 or something like that, where we have to graph by hand. We learn how to graph. We will have to find horizontal, vertical, and slant asymptote, whatever they have. So we will use this long division of polynomials then. I'll make sure I mention it so you can review your polynomial division. Your calculators can't do that. So you have to learn, I have to know, you should learn it a long time ago, the way to divide this. Good. One of the cool and important horizontal asymptote problems is the inverse tangent. This pops up in Calc 2. It pops up in differential equations. There will be maybe 1 or 2 problems here in Calc 1, but mainly you learn mathematics for future mathematics. That's for purposes of future mathematics. So if you have the f of x is equal to inverse tangent of x, its graph will have 2 horizontal asymptotes parallel like this at pi over 2 and negative pi over 2, and the function will go like that. So on this side we have that the limit of as x goes to negative infinity of tangent inverse of x is equal to negative pi over 2. And over here in blue, we have that the limit of inverse tangent of x is equal to positive pi over 2 because x goes to positive infinity. So we see that this inverse tangent produces 2 asymptotes, right? And it's stuck in between. So this will show up. Make sure you study this example to recognize when it shows up. Okay, we talked about all of this. And now I would like to present one of the, the spicier algebra situations that you might run into. And that will be it for this lecture. I hope you're not disappointed. These are very short. They don't have few things in them. So, consider f of x is equal to 3x cubed minus x plus 9 divided by the square root of I don't know, it doesn't really matter, 16x to the 6 plus 4x to the 4x squared plus 2. Doesn't matter. Let's say this is something that you would like to check whether it has asymptote or not. Horizontal asymptote. The rule that you know is to divide by the largest exponent. Now, what's the largest exponent? This is where it usually goes wrong. The largest exponent is 3. Because what's the square root of x to the 6? It's x to the 3, right? Take it for a face value. So, when that x to the 6 is in disguise over there, actually x cubed, yeah, because it's square root of x to the 6. So we divide everywhere by x cubed, but then when that x cubed undergoes square root, it will become x to the 6, and then we'll still cancel. So I am dividing by x cubed everywhere, and here is the x cubed division on the bottom. So now limit x goes to infinity. On top, what do I have? I have 3 minus 1 over x squared plus 9 over x cubed, and on the bottom I have square root of 16x to the 6 over x to the 6 plus 4x squared over x to the 6 plus 2 over x to the 6. Now, x to the 6 and x to the 6 cancel. This one goes to 0, this one goes to 0, this one goes to 0, this one goes to 0. They all go to 0. And I am left with 3 divided by square root of 16, which is 3/4. Done deal. Now, just aside, if you are having algebra issues right now, and you're freaking out what happened, I will remind you from your algebra course, square root of 16x to the 5 was solved by breaking this into 16 times x to the 4th times x. Square root of 16 is 4. Square root of x to the 4th is x squared, and 1 root on x stays. This was a standard elementary algebra problem that works with roots. Now, even easier than this would be a problem that says square root of 3x to the 4. Well, this is x squared root 3. Now, let's say I need to stuff this back in. Well, it would pick up the square because it's a square root. So we'll pick up the square and it will show up as 3x to the square squared, which is 3x to the 4th under the root, which is where we started from. So, if you are taking stuff out of the root, you get to divide the exponent. But if you are stuffing stuff back into the root, you get to multiply and increase the exponent. It's exactly what happened here. I need to stuff this x cubed inside the square root, so it becomes doubled. Let's check. If I have square root of 3, let's not use 3, let's use 7, divided by x cubed, and I want to extend the square root, the way I would extend the square root would be to say, okay, I'm going to take a square root of something square, right? Would you agree that those cancel? And you just apply that to x cubed. So now you see that it's root 7 over root x to the 6. And then another algebra rule tells me that I can combine everything under the same root. So you see that x cubed, which was not under the root, picked up the 6th exponent, and now it is. So that's the part with calculation that you have to be careful. Other than that, everything else should be straightforward. Short lecture. Bye.